Okay. I really want to acknowledge the invitation to be here today, and especially like to acknowledge also Dr. Vanessa Pereira, with whom I prepared this presentation to share with you. We are particularly interested on discussing with you issues related with water and wastewater treatment, and what can you do also for a safe reuse of water. Actually, you could say, being Earth the planet water, why a water issue? I mean, let's see, the question is that in fact, most of it is not really available for consumption purposes because it's salty water. But even with the fresh water available, I think most of the problem is not related with the amount that is available. Is of course related with the uneven distribution of this resource and the difficulty sometimes to use it in the right place. Of course, the increase of the human population also makes an extreme pressure on the needs to have water that is safe for consumption. If we look a little bit to our activities as humans, in all our activities we are producing somehow compounds that at the end will end in the water courses or water reserves from all activities, from agricultural activities, domestic activities, or industry. In all these cases, we end up with a number of compounds, a large number of compounds, and some of them are very resilient, are very difficult to be somehow managed even in nature. If we look a little bit to the numbers are a bit scary in terms of the amount of compounds that are released due to industrial production and consume. Also the amount of compounds that are also released due to intensive agriculture, use of fertilizers, pesticides, and so. And even Europe has been doing an effort in terms of restricting and legislating about the chemicals that can be used industrially with the so-called REACH agreement, but even though the number of compounds that are registered is extremely high. So as a consequence of this and other activities that are, let's say, energy related, which I will talk later, we really have a situation that we have to be concerned on. Actually, for me, this session today has been extremely interesting because we have been talking mostly about food, but actually I believe that we have to think in terms of a nexus between water, food, and energy. I think that without thinking in these nexus, it's very difficult to take any one of these problems by itself. You just consider a few examples that I have here listed for you. I mean, we need energy to treat and transport drinking water and wastewater. Water is required to make electricity. Now in the oil and gas exploration, you need also injection water. You get produced water. You know, all the problems related with the fracking technology and so water is used to produce energy. Energy and water are needed to grow food, and a number of crops are now used not for food consumption, but for production of fuels. So you have a very interlinked relation between all of them. And in terms of quality, the same is true. I mean, your water quality is very important in terms of, for instance, of the food that you produce, but also when you are producing food or energy, you have consequences on the water quality. So this system is very much interlinked. Actually, if we look a little bit to the situation now, I mean, the forecast for the population by 2050 will be something like around 9 billion people, which means that water will be really the key for food and energy security, for sure. And look that for the moment, agriculture accounts for around 70% of all water withdrawn, which means that there is very, very high pressure here, because if you want, of course, to feed everyone, there will be a very high pressure here on the consumption of water in agriculture. Also, if you think in terms of the energy and the way we produce energy, water is more and more used. So we really have a very high pressure in terms of the use of water. Of course, at the end, you may always think, okay, but we can treat water, and of course we can, but just compare how much energy you expend when you have to treat water. You see, if you have surface of groundwater, the amount of energy that you have to put in to produce a cubic meter or so is much lower than if you have to desalt water. Of course, you can do the water desalination, and we do, but still just compare. I mean, if I want to do seawater desalination, I expend around 3 kilowatt-hour per cubic meter, which is a lot compared if I have a fresh source. And of course, if we have to treat wastewater, we have also numbers that are significant. So this nexus is extremely important, and the way we think in terms of treating water is very much related with the interlink with the energies that we can have available for treating that water. One problem that we have also to think a little bit is if we compare a little bit what is the water withdrawal with the real water consumption, there is a gap between the two, which means that not all water that is somehow extracted for use is at the end being used. These are figures from late 90s, early 2000s, but the situation is not that different nowadays. And what you can figure out is that even in countries where you think in terms of high efficiency, this high efficiency is not that high. I mean, you can compare Europe with other regions in the world, or Europe and North America, and the gap between withdrawal and consumption is big. And so big means that there are factors, of course, that are more difficult to control, like evaporation or so, but that means the way you are somehow extracting water and how are you distributing it. Because if you have a simpler and shorter distribution networks, you probably can avoid part of this problem. It also is related with the efficiency of the use of water. Depends how efficient are you using, for instance, in agricultural uses or so. Okay? So we have to think on these two things. There is one point that is interesting, which is, I mean, if you look to Asian or African countries, most of the water is used for agricultural uses, you see here, okay? A little bit on the municipal and industrial water. Industrial water, not that much. And when you look to Europe and North America, you see that most of the water is used for industrial purposes. Now, what this means is that as Asian countries are getting more and more industrialized, there will be very high pressure in terms of water consumption here for industrial use. But the needs for feeding the people are still there. So the pressure on water consumption will be extremely high from these countries which have a high population also. The problem is not only of a physical water availability, it can be much more complex than that. I mean, there are areas in the world where we can consider that there is not a really water scarcity. But what is even worse is a situation where you may have water available for use, but for some reasons there is an economic water scarcity. That means that for human, institutional, financial capital, for those reasons, water is available, but you are not really able to use it and put it at the consumer. And so you may have in those regions serious problems of access to water, although the water is physically accessible. And you have, of course, regions where you are approaching the physical water scarcity, and you have regions where you have a really strong physical scarcity of water. Now, the impact of not having water, or having water with sufficient quality and safety, following all the safety regulations, is that you may really have an impact in terms of health. And just to give you a very simple example, but I think it's an example that touches all of us because you're talking about children, the deaths that can be attributable to water sanitation and hygiene, for instance, if you look to diarrhea problems in children below 5 years old, you can see that you have a significant problem here in terms of death, of people that die because they don't have really an access to water with the necessary quality. It is also a gender issue. Actually, I found very interesting because we have some comments this morning about also the gender issue here. But actually what happens in many of these countries is that it's women and children that take the responsibility for water collection. And so there is really a bit an imbalance of the way that society organized in terms of collecting the water. And so there is also a gender issue here. Of course, these This need for safety water and the lack of water in some regions has been also putting a pressure in terms of biodiversity. So there are biodiversity threats that we have to think about, because there are regions where due to the human activity, and so we are really getting into scarcity situations. So there is a threat in terms of biodiversity. And as we are also talking about the Mediterranean region, maybe a forecast, a climate forecast, and forecast models that show that the decrease in terms of precipitation in the Mediterranean region, the prospective rise in temperature in the Mediterranean region, and the water balance, which is extremely negative. So we have the forecast on extremely negative balance in terms of water in the Mediterranean region. Now, as an engineer, I tend very much to think that I can solve everything with technology, but we heard this morning a very interesting comment by Dr. Sasson, exactly that the water package sometimes cannot solve everything. So actually, I think we don't have just a scarcity of water, I think we have scarcity of other things. And actually what it seems is that we have a scarcity of accountability for achieving sustainable outcomes. We have a scarcity of organizational capacity, and of course we have a scarcity of physical resources here also. You see that the scarcity that you may have in accountability for achieving sustainable outcomes should be solved by efficient allocation and inclusive decision making. And this could have an impact in terms of water allocated to the highest value use and allocation systems that are responsive to variations of supply and demand. So this is sometimes more important than having the right technologies to do it. You need it for sure. In terms of organizational capacity, you see that at the end, if you don't have an integrated planning, you probably don't have the right tools to make the water available for people. And finally, of course, you need to have the right water technologies to build the right engineering infrastructure so you can have your supply increase and you have storage and distribution networks that work properly. Now, I will take the risk a little bit to bother you a little bit, but I'm going to talk about some of the technologies that may also help us to solve some of these problems. Because our purpose at the end is somehow to improve the way you are using water, and in many cases, the possibilities to have a water reuse. Okay? Water reuse is an issue that is, of course, technical, but is much more than that. It's an issue that involves, for sure, that there is a stakeholder in public acceptance. If there is not a public acceptance of the use of water, we cannot really solve the problem. So it's extremely important to have a clear demonstration of the safeness of the water that is reused. It is very important to assure that there is a comprehensive monitoring program, otherwise people will get afraid about what is going on. And of course, there will be a precautionary principle, because we have to really know to deal with the non-constituents. So, of course, water reuse, it's a must at these days. So we are talking about not only municipal water, but municipal water reuse for sure, but also industrial water reuse and agricultural water reuse. I don't think I'll go in detail through the possibilities of water reuse. I mean, I'm sure that you know a large number of examples that comes from agricultural irrigation to industrial recycling and groundwater recharge and so. I'm not going into detail here. And now I will like to mention to you some of the technologies, because you need some enabling technologies to deal with this, okay? So sorry for this will be my engineering part here. Okay, I'd like to share with you a little bit some ideas about the use of UV photolysis in advanced oxidation processes, biological processes and membrane processes. I'm a bit biased towards membrane processes because that's my field of interest. But of course, I'll show you that membranes usually has to be integrated in hybrid and integrated processes. Starting with direct and indirect photolysis. This is really a critical issue, and I can start with a very interesting example that came from the outbreak of cryptosporidium, and in the United States in '93, there was a number of people that died, over 100 persons that died in the United States in the summer of '93, and the reason was because the traditional treatment of drinking water for drinking water supply using traditional techniques, it was a very warm summer, it was not possible to retain all the protozoa that were present in the water, and so there was a outbreak of cryptosporidium, and that posed a problem. Now, it's a bit sad to say that that event was the one that somehow boosted the use of photolysis treatment and also boosted the use of membranes in terms of more safety treatments. Anyhow, what you can do with the disinfection by UV is that UV has a high efficiency against protozoans, or much higher at least than, for instance, chlorine has. So if you go through a UV treatment, you can decrease the chloride zone, and if you decrease the chloride zone, you decrease the risk of formation of disinfection byproducts, which can have detrimental impact in terms of human health, like carcinogenic compounds or so. Also, UV can be used for the degradation of contaminants. You can do it either through direct photolysis, where you have direct irradiation with UV, or indirect photolysis, where you use, for instance, titanium oxide or hydrogen peroxide or ozone. You create free radicals, and these free radicals can degrade the organic matter you are interested in to degrade. Just to call your attention, usually when you have a solution, you also create some new problems. And here you can see that in some cases, the percentage of degradation using UV can be extremely high, so you can really degrade the compounds you may be interested in. But we have to be careful, because sometimes you create subproducts from this degradation. And so these subproducts can accumulate, and in that case, you really have to monitor what is going on. So be careful always. I mean, you solve something, but you have to take care of some other problems that you may create. One of the areas that has been really growing a lot, I mean, it's obvious. I mean, we saw that in many situations you don't have really access to fresh water, so salty water is a fantastic resource for producing drinking water. You probably are familiar with all the programs for seawater desalination, and nowadays most of the plants that have been commissioned using a technology of reverse osmosis. And the reverse osmosis use typically polymeric reverse osmosis membranes for that, through a process that actually can give you, let's say, a cubic meter by something like 40 cents of a dollar per cubic meter, which is quite affordable for many regions. Israel has been probably the champion in terms of the plants installed for seawater desalination. So that it's the largest plant installed now. The previous largest was also in Israel, the Ashkelon plant. So this is a mature technology. It's working, it's a mature technology. But what is really fun in the science, in the research, is that even when you have a mature technology, you always start thinking on something else. So the developments here now are in terms of increasing or improving the pretreatment, so you can have a better process running on. Improving the monitoring, so you will be sure that you don't have leaks or so through your reverse osmosis process. And the most challenging problem nowadays probably is the fact that once you are doing reverse osmosis and once the membrane has a lifetime of 7 years or so, at the end you have to dispose them. So what we are concerned now is ways of reusing the membranes themselves in a way that we are not creating a different waste now, which will be a polymer that may remain in a landfill. In terms of drinking water production, you typically, probably the traditional way is that, for instance, you have a source of water, which can be groundwater or surface water. Typically, you do a relatively light disinfection, which can be ozone, but it also can be a chlorination or so. And then what you do is that you do a mixing, do flocculation and the sedimentation, sometimes a sand filtration if it's necessary. So this is the typical way you do it. And then you have to do a chlorination for final disinfection before going to the distribution system. Now the problem here is that you can do this process, but usually your chlorination or final disinfection has to be relatively strong, because you have to assure that you don't have microbial growth in the distribution system. Now what you can do here is the following. As I mentioned you before, if you do chlorination, you may get halogenated compounds, and so you can have disinfection byproducts, which can be carcinogenic or so. So one of the ways to solve this actually is, instead of using chlorination, to use UVs in advanced oxidation. But also the other thing that you can do is to have a hybrid process, and you have a multi-barrier approach then. With a multi-barrier approach, what you do is that you use a filtration with a membrane process, not as tight as reverse osmosis, but nanofiltration, and then you do the disinfection. Hybrid processes usually have an advantage. I'll give you an example of using a hybrid process. We talked previously about the degradation of organic compounds by UV radiation, but one very interesting example of indirect photolysis is a situation where you use, for instance, titanium oxide particles in suspension and you irradiate. Now, you know that nowadays there is a concern of nanoparticles in the environment. So if you release nanoparticles into the environment, it can be really creating a problem. But what you can do is to combine the use of suspended particles of titanium oxide with a barrier, which can be a membrane, that retains the particles inside, so you keep them in a restricted physical space. And by doing so, you can obtain a permeate, which is treated water, with a very high reduction in terms of these compounds, typically above 85%. And the retentate, which is retained here, as it is kept in this loop, I can adjust the residence time here, and I can get also very high degradation rates on the retentate. That means that I'm treating both streams, the brines or the retentate, which usually are a problem, and the permeate, which will be the treated water. This is a typical wastewater treatment. So in most places where you live, what you have is the scheme above. Okay, so typically what you have is that you have a wastewater, it can be municipal wastewater. You have a primary treatment of the wastewater, and then what you have is a reactor, which is activated sludge reactor, it's an aerobic reactor, where you degrade organic matter and nitrogen compounds. And of course, then you have to clarify, and you have to filter, and you have to disinfect. And one of the really breakthroughs in the last years is the use of membrane bioreactors, where actually what you do is you put this box here inside, so you submerge the membrane bioreactor inside the activated sludge. And as what you can do here is that you are doing the biological reaction at the same time you are filtering the water. So at the end, you have the permeate, which is ready for consumption. I probably go very quickly here just to show you that membrane bioreactors can even be designed to treat specific problems. We can, for instance, have a process specifically to treat with ionic mercury. Okay, so you can transport ionic mercury, oxidize it to, reduce it to metallic mercury, and then to evaporate it. Okay, I'm going to speed here. Can do the same for arsenate. This is a very interesting project because it's relevant for Pakistan and India. So we can take care of waters contaminated with arsenate. And my final comments will go into something which is different, because we have been talking about reuse of water, but we should also think in terms of reuse of other components that are in the water. And in this case, what I want to call your attention is that reuse and waste streams are not just an environmental burden. They can be a source of value if you have the technologies to recover them. So we can recover nutrients, bioactive compounds, but you need the technologies for that. Just to give an example, because you've been talking about food, in terms of agro-industrial residues, there is really room for recovering extremely highly valuable compounds, okay? Some from small molecules to large molecules, and even biopolymers. My two last slides, okay? This is a discussion that we have been doing already a little bit for the food production. It's an extremely important discussion also for the drinking water or wastewater treatment, which means centralized versus decentralized water production. There are many situations, I believe, that decentralized systems will really be an advantage because you can have a better point of source treatment, and you have less losses with distribution, and so this has implications in terms of distribution. So if you go to decentralized systems, you will think in terms of reuse of water, reuse of nutrients. Within some regions is essential because you need them as fertilizers. And you have to do really a membrane integration. I give you a very simple example. You may use a membrane unit, but if you really wanted to have it operating in isolated places where sometimes you don't have electricity available, you have to do it in a self-sustained way, sometimes with solar panels, and without a skilled operator, so remote operation using ICT. And you have to get the involvement of the local community. That is absolutely necessary. Okay, I just finished. I hope you know the red queen effect. The red queen effect, I can read it for you. In this country, you see, it takes all the running you can do to keep in the same place. If you want to get somewhere else, you must run at least twice as fast as that. I think we are exactly in this situation in terms of water and the environment. I think you really have to run twice as fast. Thank you so much for your attention.
Thank you, Professor. If you have some question, some quick question before going to the lunch, but we have a little bit time to ask. If nobody has question, I have a question for you about the medicines residue in the water. I saw a presentation some month ago saying that main of the quantity of medicine that were taken by people are found in the water, in the seawater or in river. Do you have some information?
Well, what I can tell you is that the problem of compounds that are used for human health, I don't think it has been treated very carefully up to now. And the reason is very simple, because actually what you do is that in a pharmaceutical company you can have a dedicated wastewater treatment, and that is fine. But in most cases in hospitals you don't do it, and of course at home you don't do it. So we have been working, for instance, on neoplastic agents, and the problem with neoplastic compounds is that you go to the hospital, you do your treatment, and you are sent back home. I mean, if you could stay at least 2 hours more at the hospital, and if they could recover your biological fluids in the first 2 hours, you could collect those wastewaters, you could treat them in place, you could avoid the release of these compounds into the environment, because we are talking about compounds that up to now the treatment that has been suggested is incineration. So we are talking about purely recalcitrant compounds. There are technologies that can take care of that, but it's extremely important that you are really going to the point of source of the emission. Yeah.
I have a related question. It's not medicine, but about drugs. There was a recent survey in France and in detection of cocaine, amphetamines in wastewaters, and they found a lot of these drugs. So is it easy to get rid of these drugs?
No, it is not easy at all. I could tell you about some of the attempts that have been done. Probably one of the most, I would say, effective will be to combine a membrane bioreactor with a reverse osmosis system. So there have been some studies on that. So the idea here is that you take the effluents that contain these kind of compounds, you go through a membrane bioreactor, so you are expecting that the microorganisms that have involved in the membrane bioreactor will take care of most of them, and at the end you do a polishing by using a reverse osmosis, which is a very tight membrane. In principle, only water should go through, although it's not completely true. And then the retentate will have still, in some cases, these compounds that were not completely degraded or so, but we are now talking about a very much smaller, let's say, volume or so. But this is a difficult problem. And I think then, as much as possible, we should try to have solutions where we don't mix effluents and you really try to treat them at the point of source of emission.
What do you think about the contribution of research on nanotechnologies in treatment of water? Do you think is it very promising, or?
I would say, well, let's see. I can say that in general, when I'm talking about membranes, in many cases I'm talking about nanotechnology, because usually membranes, what they have a support and they have an active layer, and this active layer usually is produced using nanotechnologies based approaches. But if you think it in terms of nanoparticles, for instance, I think that really the concern is that we are using nanoparticles already nowadays in many situations, and there is a growing concern in terms of the releasing of these nanoparticles to the environment. So that I think that really one of the concerns that we have to bear in mind very carefully is that we will end up with a serious problem if we don't start taking this seriously. And one of the things that I was suggesting here somehow is the possibility to have a multi-barrier system. Let's say, I mean, you use a system where you have nanoparticles, but you probably have to have a barrier that is able to retain those particles. So you see, in many cases we are talking about particles that are relatively easy retained by, I would say, ultrafiltration or even nanofiltration. Maybe ultrafiltration will be sufficient. Ultrafiltration is sufficient for virus retention, so it will be sufficient here also. So I think that this is really a question of awareness in first case, because I think there is really a problem here that people should be aware. And then, of course, on the political, let's say, will to take this problem seriously and to install ways of treating this kind of situations. Because technologies for that, they are already available.
Okay, a last question before going to the lunch. And then you can discuss with Professor during the lunch.
Okay. Thank you very much. I have a question. Do you think about treat the water which is coming with the oil? We have a huge of water coming from the ground when we exploit the oil from the ground. So
Yes.
this is this water, of course, containing many organic compounds. So do you have any program to treat this water for reusing for irrigation or anything?
Okay. If we are talking about situations where you have oil in water emulsions, and in some cases you have oil in water emulsions, I'm thinking in some cases of the oil and gas industry where you have emulsions. Some industrial uses for machinery production, you also have oil in water waste streams. And also in some, let's say, food applications like vegetable oils or olive oil whatsoever, you also have oil in water waste streams. For all of them, what you can do, for instance, is to retain the oily fraction, but now I'm talking about retaining the microemulsion. There is still a compound which should be below the solubility limit that will be present still in the water, yes, because you are removing the microemulsion, but the soluble components will stay. So probably you'll have to go to a system where first you remove the excess, or let's say the microemulsion, the oily microemulsion, and then you have to go to a process where you probably have to degrade the organic compounds in the water. And for that, most probably a bioreactor or a membrane bioreactor will be the approach. So this will be for sure a combined method for doing it. Actually, at this very moment, me and Vanessa, we are exactly working a project for oil in water emulsions streams. So this is something that Europe is concerned on, because there is many industrial activity where this kind of effluents are produced. And yes, I mean, the answer is there are technologies that should and could solve this problem.
Okay, thank you. And now we have to finish because Sandra will have problem with the earth. Okay. We want to thank all the participants of this morning, all the speakers of this morning, and essentially Dr. Crespo. And we have to come back at 1:30 in the room. Please have a nice lunch.